Yeah, hello everybody. Today my friend Fahri Muhammad and I, Alif Ramadana, will explain about Voyager 2 calculation for a Jupiter planetary mission. So before we continue, let me explain about planetary mission. Planetary mission is a mission of a satellite that have objective to observe planets near the Earth. For example, Mars, Jupiter, and etc. In Voyager 2, it has a mission to observe Jupiter, Saturn, Uranus, and Neptune, also doing an interstellar mission. Voyager 2 itself launched at 1420 UTC on 20 August 1977, and it reached Jupiter for observation on 8 July 1979 with a pericenter radius 700 to 21,670 kilometers. For satellite data itself, Voyager 2 is produced by Jet Propulsion Laboratory in USA and launched in Space Launch Complex 41, Cape Canaveral, Florida, with a latitude is 28.5621 degree and longitude minus 80.5772 degree. The satellite launched with a launch vehicle that is Titan 3E with voltage main thruster with a maximum load at 145,000 kilograms. This is the data for mass and ISP for launch vehicle. This is the picture for launch site and launch vehicle. So in this presentation, we will explain about how to calculate the transfer orbit calculation for this satellite, so it can get uh, get to its mission effective and efficiently. So in the first step, we need to calculation the velocity of a heliocentric orbits, which is there is Earth and Jupiter. Also the calculation for the transfer orbit itself. For Earth velocity, we know that from data radius perihelium of Earth it is 1.471 times 10 to the power of 8 kilometer, and with apohelium 1.521 times 10 to the power of 8. So with those parameters, we can get the parameters of Earth with for the revolution to the Sun. We can get the semi-major axis 1.4196 times 10 to the power of 8 kilometers. And we can also get E with this equation 1 minus radius pericenter of Earth, radius perihelium of Earth divided by semi-major axis, and we can get 0.167. From these parameters, with from this parameter with a mu sun 1.327 times 10 to the power of 11, we can determine the velocity of Earth on perihelion and aphelion. For perihelion itself, with this equation, we can get the exact number for 30.285 km per second, and we also get a velocity on aphelion 29.289 km per second. We also need to calculate Jupiter velocity. From data we can get from internet, we know that radius perihelion of Jupiter is 7.405 times 10 to the power of 8, and its aphelion is 8.165 times 10 to the power of 8. So we can get semi-major axis 7.785 times 10 to the power of 8 kilometers. We also get that the eccentricity is 0.049. With a mu sun is 1.327 times 10 to the power of 11, we can get that the velocity on perihelion with this calculation is 13.710 km per second, and its aphelion is 12.433 km per second. Let's back to the picture before. This is the position, I mean the transfer path for Voyager 2. We know that the satellite launch from Earth and then travel to Jupiter, Saturn, Uranus, and Neptune. So how it can travel to Jupiter and the other planets? We assume that the satellite is using Hoffman transfer orbit, which is used the ellipse orbit between Earth and Jupiter. We also assume that the satellite position is on Earth, that in perihelion, and transfer to Jupiter in aphelion position. So from this parameter, we also need to determine that there is a distance for satellite to escape from the Earth, and there is a distance for satellite to enter the Jupiter. With this, we will call it D. We assume that the escape is equal 10,000 kilometers from Earth radius, and the arrival is equal 1 million. So the perihelion and aphelion of satellite transfer orbit are 1.47111 times 10 to the power of 8, and its aphelion is 8.175 times 10 to the power of 8. From those from this distance, we can know that the parameters are for semi-major axis of the satellite. You know that it is 4.823 times 10 to the power of 8, and its eccentricity is 0.695. Then from this parameter, we can know that the velocity of satellite in perihelion is 39.102 km per second, and the velocity on aphelion is 7.036 km per second. Then the next step is we need to calculate the delta velocity of the heliocentric orbit. It is the velocity difference that happen in um, transfer orbit, and Earth or Jupiter orbit. In first delta velocity, we can calculate it by adding the velocity of pericenter perihelion of transfer orbit minus velocity of Earth. Now we can know that it is 8.817 km per second, and the delta v is the velocity of apocenter Jupiter minus velocity of aphelion transfer orbit. And then the next step is we assume that satellite is orbiting in circular orbit. So before it tried to orbiting to reach Jupiter, it parked in a circular orbit that we assume it is 80,000 kilometers from Earth mass. So with mu e Earth is 3.986 times 10 to the power of 5, we will get that the velocity of its satellite is 7.058 km per second. Also from V infinity, which is delta V e Earth transfer, it is 8.817, so the energy characteristic is 77.736 km square per second square. So how we determine the velocity needed to escape from Earth? From V infinity before, we can know that the semi-major axis for hyperbolic trajectory is minus 5.127. I mean minus 5,127.58 kilometer, and its eccentricity is 2.192. So the escape velocity can be calculated as 14.429 km per second. Then when is the time that it need to launch from Earth parking orbit to transfer orbit? The maneuver parameter for a hyperbolic is delta V escape is delta hyperbolic minus velocity in hyperbolic minus velocity for circular orbit, and we can get it is 7.371 km per second. Also the pH1 or the distance of circular orbit is 8,000 km, and the theta that or the theta that need to launch the satellite is in 2.0545 radian or we can get it alpha is 0.474 radian. I think that's all from me, and the next step will explain by my friend Fahri. Thank you.